agricultural economy. So, okay, very good. So that's the part on optical recycling. Now I want to spend the rest of the class talking about a technology that can be applied here. But before I jump into this, let me stop and see if there are any questions first. So as a brief summary, I hope you have a chance to appreciate, the identification of an important problem and how folks are thinking about, from an engineering perspective, how you go about solving that problem, applying optics. But at the same time, there are policy issues and political implications that affect those technical choices as well. So all of these are really kind of connected, right? And then hopefully you can appreciate that. Now, what I want to talk about the rest of the class is a particular implementation of a spectral imaging technology that my lab has been working on for several years, but it's an important example of optical engineering, slightly different than what you've seen before, that is applicable to the application of optics in resource recycling. Okay, so let's start with some very, very basic background. If we think about how cameras take color images, like in the case of your phone camera, the way it works is that, of course, cameras contain optics, right? If I draw a very simple picture of a camera, I have a lens and I have a sensor, right? I have a lens and a sensor, as we learned in the first half of the class, and it will take a picture of this arrow and project it onto the sensor. Now, of course, the sensor typically is color blind. In other words, it does not distinguish different colors. It just absorbs all photons. As long as the energy of the photon is larger than the band gap of the material used in the sensor, typically silicon, right? However, how do you see color? In order to see color, you need to somehow distinguish the colors. And for human beings, as we saw before, we are interested in red, green, and blue primary colors. So we need to be able to distinguish these red, green, and blue. And this is done by placing something called a Bayer filter array, which looks like that, on top of your silicon monochrome sensor. Now, the Bayer filter array, as you can see, has a blue channel. And what that blue filter does is that it absorbs all other light, like red and green, and it passes the blue. So if I were to look on my signal, I have a blue signal here, and I have a green signal here, I have a red signal here, and I have one more green signal. I have two green signals, as I mentioned on our talk on the displays. We had a very brief talk on this. Is because our human eye is most sensitive to green, so you want to get as much signal as possible from the green part of the spectrum. Now, of course, this data, and by combining these two, you end up with the color sensor, which looks like that. Now, the data from this color sensor, of course, is what's called mosaic, which means that you see the blue channel here, green channel here, green channel here, and red channel here. And somehow we need to combine this in using some interesting matrix mathematics, actually, which we won't talk about, to create the full color image that you typically see when you take a picture with your phone. Okay. Now, in the case of resource recycling, we want more than three colors, right? We want the spectral information. Sometimes we want it in the infrared, which, it's outside the blue, green, and red. And for these cases, we need wavelengths greater than 3. In this case, the typical solutions are something called hyperspectral imagers, which are shown here. And they use either tunable filters, where you simply change the wavelength of light that passes through the filter over time. So this is multiplexing with time. Or the push-broom plus grading of prism. I won't talk too much about this. Tiled filter array, which is basically taking this idea. This one has a 2x2 filters, and maybe you can make that bigger. So you can do 5x5, so you get 25 wavelengths, right? Here I'm getting 3 wavelengths out, but I have 4 channels here. Here, maybe I can get 25 wavelengths out. And there are coded aperture ideas, which I won't talk about either. So I'm going to talk about a particular approach that we have been developing in order to do this. First, let's think about what the system looks like. So, oops. Where is this? Okay, it's fine. Good. So here is what the system looks like. We'll start with the object, which is my object now. Remember, that's a conveyor belt, or the scene on the conveyor belt I'm looking at, which has a reflectance, which is a function of both x, y, and lambda. So it's a three-dimensional function. And then I have a lens, and then I have a sensor. Right, those are my objects. Now I'm going to introduce something called a diffractive filter array in front of the sensor, which is like the grating that you saw before, or the diffractive optical element we saw before. And all it does is, instead of forming a point spot, as shown here, I form a blurred spot, as shown here. So remember, a lens, I'm going to draw this in cross section, will take a point and form a point. This is what we know from geometrical optics. But now I'm going to introduce something in front of this. Like, this is what I call my diffractive filter array. Instead of forming a point here, I'm going to blur this because I'm diffracting the light. But what's special is that I'm going to blur it in a very specific manner that changes the shape of that spot as a function of wavelength. Okay. And you can think about the mathematics quite simply from a very simple matrix multiplication. So the way to think about it is that, okay, I have a measurement, which is my monochrome image, okay, which is my eye. That's my measurement. Let's think about that as a column vector. Then I have my input data, which is this S, hyperspectral data, that is also a column vector because I'm going to just open it out in x, y, lambda, and I'm going to index it down. And in between, I have a system matrix, or it can be thought of as a spatial spectral points per function, or the transfer function. This is a matrix, right? And I can write this as a matrix equation. Now, what is happening here? I am going to measure this. Right? That's my image from the sensor. This is my unknown. I don't know what my hyperspectral data is. And this is a transfer matrix that I can actually measure if I'm very careful about it. So I know in this system of equations, of course, a matrix is, this multiplication is simply a system of linear equations. If I know two sides, I only have one unknown, I can invert it and solve for it, which is exactly what's shown here. So this is my unknown, this is measured by simply inverting the matrix, multiplying the inverse on both sides, I get this, right, this equation. Now, of course, solving this equation in practice is very complicated. I won't go into the details. There's something called regularization that you have to apply, which is something comes out of linear algebra. Actually, if you're interested, I'm going to teach a class on this next semester, but in the interest of time, I'm going to skip that and talk about the actual experiments themselves. This is what the camera looks like. So we actually built them. So just to give you a sense of what it looks like. First of all, this is the final camera over here. It looks like a normal camera. It's a scientific camera. Otherwise, it's fairly normal. This is the lens here. You can see. Now, if I remove the lens, what you see is here. This is the diffractive filter array on the sensor. The sensor is behind it. It's kind of hard to tell, but it's there. And the diffractive filter, or the DFA optical microscope is shown here. This is what it actually looks like. We actually make this in our nanofab. And then this picture is just macroscopic picture. This is a microscopic picture. So you can see it's pretty small. It's repeated tiles, and it's transparent. It's a really interesting device. It's, of course, engineered in a very precise way. And the way we fabricate is also interesting. I'll mention it briefly. We use something called Grayscale Lithography. I'll actually talk briefly about this when we talk about spectrum splitting. But this is an interesting way to make optics. So something you should be aware of, where we use a substrate, which is typically glass. We coat it with something called photoresist. Now, photoresist is just a polymer that reacts to light. And then we put a laser beam with different power. So here I have more light, you have less light, and you have even more light. So that's why it gets darker. Now, by changing the energy that I'm depositing into the photoresist, I can, after a development process, it's a chemical process, I can create different topographies. So here I have more energy. Here I have slightly higher energy, and this is I have my standard energy. So I can see I can create deeper and deeper structures. And I won't talk much more about it, but this is an approach that allows one to make very complex structures as shown here, which, by the way, you can see some geometries here which look like skyscrapers. So that's how you make those things. Now, by the way, interestingly, these kinds of devices actually exist in your phones today. These are used in your holograms that are used in the Face ID of your iPhone or the facial recognition system of the Android phone. These are made at very, very high volumes today. I'm going to skip that. These are examples of devices. So here's a picture of some devices that we made in our lab. The top pictures are the optical micrographs. The bottom pictures are atomic force micrographs, where you can see these very complex three-dimensional structures. And I'm going to skip this, but I won't go through the details of the measurement, but this is the way we measure the matrix A, which is the transfer function, if you remember. Remember, the transfer function itself transfers I is A times S. Now, I is a three-dimensional matrix, right? That's X, Y, and lambda. S is another three-dimensional matrix because I have X prime, Y prime, lambda. X prime, Y prime being the coordinates on the object plane, X, Y being the coordinates in the image plane. Now, if I were to actually work this out, this becomes a six-dimensional matrix. X, Y, lambda goes to X prime, Y prime, lambda. Of course, actually, because the lambda is degenerate, they're the same, it becomes a five-dimensional matrix. Nevertheless, as I said before, we actually can unroll it into a two-dimensional matrix, but at the end of the day, you still have to measure five-dimensional parameters. So it turns out to be not such a simple problem. But anyway, we can measure this. It's kind of a tedious process. But after you measure it, you can actually solve the problem for S. So if you remember, I equals A times S. A was measured. I is this. This is an example of an I. A was measured before. And S is this data set here. So in this example, this our object was a letter H with the blue here, red here, and green here. And the idea was to take a picture of it. This is what you collect. Apply the algorithm, which is basically inverting this. S equals A inverse of I. So apply some linear algebra, and you get this full three-dimensional data set as shown here. Which, of course, if I'm going to, oops, get rid of this. Is if I take this spectral data, I can represent this in an RGB, which is shown here. So it's easier for a human being to understand it. But you can see in the spectral data, so if I can, example, the reds are here, the blues are here, the greens are here, right? So you can see the parts being separated out. So this would be an example, okay, if I want to separate out even more detail than red, green, and blue, let's say I have a pistachio which emits in the green at this wavelength, whereas I want to separate it from a twig or debris which emits somewhere else, right? So let's say here, I can actually separate them out. That's the idea. Let me show you a couple more examples, and we can actually do this really fast. So this can be done in a video, for instance. I don't have the video here, but you can imagine doing this with a conveyor belt and so on. This is another interesting experiment we did with the letters Utah with different colors, and you can see that you can separate out the different colors very, very quickly, very, very precisely as well. Again, keep in mind, this is the raw measured data. So this is my I, and this is my S. Okay, remember again that I'm actually inverting this. So I is measured, A is measured, S is calculated. I can also do it very precisely with very high spectral resolution. In this example, I'm showing you 12 nanometer spectral resolution, which is important for, again, distinguishing different kinds of plastics, for instance, relevant to our lecture today. This is showing different colors. So the black curve is a reference spectrometer, whereas the blue curve is a reconstructed result. Here we're showing that we can get very good spectral reproduction with error of something less than 10% or so across the entire visible spectrum, in this case between 400 and 750 nanometers or so. Actually 400 to 800 nanometers. We can do pretty good spatial resolution. This is a way to measure spatial resolution is by making smaller and smaller objects. In this case, we're looking at horizontal and vertical lines at different colors and squeezing the lines closer and closer together until we cannot resolve them. This is just showing that. So here you can see the conventional cameras starting not to resolve, whereas here we can still resolve this somewhat with our computational approach. Again, same kind of thing in the vertical direction, different colors and things like that. I won't talk too much about the MTFs, but this is something I think you probably covered in the talk on geometrical optics, but it's an important metric to characterize imaging systems and lenses and so on. MTF represents the contrast in terms of spatial frequency. So higher the contrast, the better the performance. Effective noise is actually very important in all these applications. In fact, in many imaging applications and sensing applications, noise is the key limiting factor. So this is only a simulation, but gives you a picture of what happens if you have very noisy picture. The reconstruction starts failing. This is plotting the average error, spectral error in grayscale units versus the SNR. So as SNR drops, of course, as SNR increases from left to right, the average error drops, of course, right? So with lots of noise, the average error is high, but so the low SNR, six or so, but very high SNR, of course, the error is very low. You can get very beautiful, very precise images. So it's an important analysis to understand, because, of course, in a real life scenario, like you saw with the example of the grapes, there are all kinds of grapes, and the light, and you might end up with a situation where the lighting is not just right, not perfectly uniform. So you could have all kinds of noise, and there's of course noise in the sensor, noise in the illumination, noise in the lenses, and so on. Right, so you have to account for all these situations. This is extremely important, because when you have to deal with very fast processing, when these conveyor belts are going extremely fast, remember the exposure time of your camera also has to be really short, right? So as you probably know, from very short exposure time, you end up with lots of noise in your data. So how do you deal with that? Turns out to be a very important, actually, computational problem. Nowadays, of course, people deal with this in machine learning. This is a more detailed slide on the noise. I'm going to skip that, not terribly important. This is an interesting experiment. I'll just explain very briefly that you can actually not only image visible bands, but you can also image invisible bands, in this example, a near infrared band. So the experiment is very simple. We took an iPhone screen shown here, and we shown a near infrared laser on it. So that, of course, the near infrared laser is invisible. So you can't see this. This is invisible to the human eye. But with this particular camera, because we can actually extract those different wavelengths out, you can actually see it. In fact, if you look at this is our S here, which is again A inverse times I. You can see that the laser indeed shows up at 850, but not in the other channels, right? You don't see them anywhere else. You can see the T, which is green. And of course, you could reconstruct the images as shown in the bottom, where you can separate out the green T from the near infrared laser spot. And there's no crosstalk, which is very nice. This is, of course, an important problem, because this 850 nanometer laser is a very interesting wavelength, because it allows you to essentially do a lot of things that you can't do with visible. For instance, you can penetrate deeper through snowstorms. So if you're in a self-driving car, you probably can see farther out. You can see deeper into tissue, so it's important for biomedical applications, and there are a few other applications related to that as well. There's a lot of really cool stuff happening in this area, but I just want you to be aware of it. I'm going to skip this, not terribly relevant for this particular class, and then let me just end with one result. So This is an example of an image we can take where we are taking a scene. Of course, you look at this, you see lots of different channels, right? You see channel of 425, 500, 575, 650, and so on. But of course, as a human being looking at this, this is a little bit meaningless. But a machine, this is actually very useful. Now, of course, the machine can translate this three-dimensional information into human readable information as shown here. So here is the translation of the human readable information. And this is a reference image of the iPhone camera. This is just a Playmobil toys, as you can see, right? And this is our reference sensor, raw sensor image. This is my eye. This is my rendering of a S in RGB. And this is just the ground truth. So again, S is simply A inverse times I. Okay, I think with that, I'm going to stop. There's a lot more we can talk about, but I think in the interest of time, and I don't want to overwhelm you to too many technical details here. I just want to show you that these kinds of optical innovations are a little bit different than what we have talked about, but we're combining diffraction with computational approaches, right? Machine learning and other kinds of approaches in order to be able to solve this problem of very fast hyperspectral imaging in order to, for instance, do sorting and resource recycling and things like that. So that's another example of an innovation that is happening that's actually happening in Utah. So, and I think with that, I think we'll end a little bit, a few minutes early today. And let me stop and see if there are any questions. I should go back. Before we end, I just want to go back to the schedule, make sure. Okay, are there any questions, first of all? Vikata, you can still hear me, right? Hello.
Sorry.
Oh, wait. Okay, sorry, I had turned down my volume. Okay.
Yeah, they're fine, I guess. Yeah.
Okay, great. So then we'll see you on Thursday, and just keep in mind that the assignment 5, I forgot to mention at the very beginning, which is the first iteration of the canvas. It's due next Tuesday. It should be relatively easy because you should have done most of it in class, but I would just clean it up, maybe put it into a PDF. You can maybe meet with your teammates for 15 minutes, 20 minutes, kind of finish it up and submit it. But of course, like I said last week, I should remind you that there is another assignment coming down here, which is assignment number 8, where you'll need to submit a final version, which is due December 7th, so which will come very fast, so don't ignore it. But that requires you to do some interviews. Customer interviews. You need to do at least 3 customer interviews. I will post more detailed instructions later. But the idea is to do the customer interviews and iterate and improve on your initial version of the canvas. Okay, was there a question? I thought I heard someone.
No, I guess. Yeah.
Okay, great. All right. Take care. See you all on Thursday.